Welcome to EDU World Space.
Problem 7.62, we have a 3 kilogram block that's connected to two ideal horizontal springs, K1 and with spring constants K1 and K2, and the system initially in equilibrium, so it's at rest right here. And the block is then pushed 15 centimeters to the right, so from 0 it's pushed 15 centimeters this way, and it's released. And we're asked A was the maximum speed of the block, and where in motion does the maximum speed occur. Okay, so I'm going to immediately tell myself that where in a motion does maximum speed occur. So for these springs, since it's harmonic motion, the maximum speed is going to be when it passes through the equilibrium position. So we've stored some energy by pushing it to the right, and that energy is all going to be elastic potential energy. And when that elastic potential energy is released, the mass moves towards the position at x equals 0. And at that point, the springs aren't stretched or compressed at all, and the energy is then all going to be kinetic energy of the block. So we need to relate the kinetic energy of the block at this point to the elastic potential energy when it compresses K2 and stretches K1 15 centimeters to the right here. So let's first find out what that total energy is. So I'm going to write down that's E1 as one in the state E1 over here, and that's going to be equal to U elastic from stretching spring 1 plus U elastic from compressing spring 2. Okay, so then that's just going to be equal to the elastic potential energy of each. Okay, so we have K1 and then times 15 centimeters. That's how much we stretch K1, spring 1 squared plus 1/2 K2, 15 centimeters squared again. Okay, so then that's going to be equal to simply 1/2 15 centimeters. I'm pulling 1/2 15 centimeters squared out, and we're just left with K1 plus K2. Okay, and then following our units, these are newtons per centimeter. This is centimeters squared, so multiplying those together, we get newtons centimeters. So that gets us 5062, 62.5 newtons centimeters. And then that's equal to 50.625 Newton meters, and Newton meters is equal to joules there. Okay, so that's our units of energy. Okay, so I've already discussed that that this is going to be energy that's going to be equal to the kinetic energy at the equilibrium position. So we have K2 is going to be equal to 50.625, and if I didn't make that clear, K2 is going to be when it's at this position here, and K1 is when it compresses this K2 spring. Okay, so then that's going to be simply writing down 1/2 mv2 squared is equal to 50.625 joules, and then you can solve for V2, and that's going to be 5.81 meters per second. The mass is just 3 kilograms. Okay, so we have part B. What is the maximum compression of spring 1? So for maximum compression of spring 1, there's going to be a symmetry in our calculations, and we can immediately just say, oh, it's going to be equal and opposite to that, but we had to show it. So here we can write down that we have the same energy as before. We're assuming no friction losses, so it's the energy here when it compresses spring 2 and stretches spring 1. It's equal to the energy when it compresses spring 1 and stretches spring 2. So we can write down that E1 is going to be the same energy as when it's at position 3, and that's going to be equal to 1/2 K negative x. Here we're stretching it in the opposite direction, so we need to write down what that is, but it doesn't matter since it's squared. 1/2 K2, this was K1, negative x squared, And since this is essentially is symmetrical in how we calculated it before, same k1 and k2, but x is just negative, but we square it anyway, so it doesn't matter. This means that we get x is equal to 15 centimeters.